So far, we have only looked at situations where we have a single eigenvalue that goes through zero, meaning it's a real eigenvalue and it's only a single eigenvalue. That generated a one-dimensional center-manifold, and we got various kind of bifurcations. Well, in general, there could be multiple eigenvalues that go through zero, or it could be a complex pair. So in both cases, the center-manifold would actually be not one-dimensional, but higher dimensional. And so we want to look at that. So let's first look at oscillations at a complex pair of eigenvalues, and in which case there will be a two-dimensional center-manifold. And let's see how we would deal with that. And well, eigenvalues. So we get 2D center-manifold. Let's take a concrete system just so we have something in front of us. We'll look at that in different ways. So it's, we'll get back to it later again. So let's say we have x dot equals minus x minus y plus 2y squared, and y dot is equal to 2x plus 1 plus mu times y minus 4xy minus 4y squared. So it's some dynamical system, quadratic nonlinearities. And when you make the linearization, you find out that it has a complex pair of eigenvalues going through zero, not through zero, crossing the imaginary axis for mu equals 0. So at mu equals 0, you have eigenvalues lambda 1 and 2 being plus minus I. And there are two eigenvectors, which if you calculate them, one is minus 1/2 plus I/2 and 1, and the other one is 2, but V2 has a minus sign here. Okay, let me actually call them V tilde because I'm going to use other vectors in a moment. So we're interested in describing this now in terms of a center-manifold, and that center-manifold is real, so we have to make first make these eigenvalues real, not eigenvalues real. No, the eigenvectors, we have to make real eigenvectors out of those. And so we make just a linear combination of these two guys, which amount essentially to the real and imaginary part of V1. So we introduce V1, which is V1 tilde plus V2 tilde with 1/2. That's going to be minus 1/2, 1, and V2 is 1 over 2i times V1 tilde minus V2 tilde, which amounts to 1/2, 0. So there are two real eigenvalues, and it's easy to check that indeed the space spanned by these is invariant under dynamics, because if you take your linearization L and apply it to V1, after a little algebra, you see that's minus V2. And if you apply it to V2, then you get V1. And so if you have an equation dV by dt equals LV, then this evolution, because L has this property, this evolution stays in the space spanned by V1 and V2. Well, of course, you can say that that was pretty obvious to start with because we're only living in 2D. That's true, but this statement is true in general, that if you have these, even a higher dimensional system, you have these two eigenvectors spanning that complex space. And if you combine them like that, you get a two-dimensional subspace, which is invariant under dynamics, and that's the center eigenspace. Okay, so what we'd like to do is now, the picture, maybe I should draw that picture once more that we have in mind. It's just now would be in higher dimensions. So we have our system XY. Well, when we had a single dimensional center-manifold, the situation was that we had a center eigenspace, which was, say, the x-axis for simplicity, and the center-manifold was tangential to that, and then we described y as h of x. Okay, and so what I mentioned that because what we did then is we used the coordinates on a center eigenspace to describe the system. And so that's what I want to do here too. So if you describe the coordinates, which is x and y, in terms of v1 and v2, you get something like, you can write x and y. I simply write it's like a u times a v1 plus v times v2. And if you write that out, it simply gives you minus 1/2 u plus 1/2 v, and here u. So that means we can now rewrite the equations that were originally phrased in x and y, which are just some coordinates. We can now rewrite them in the coordinates u and v, which span the center eigenspace. And so that's the idea. And so if you do that, let me skip the algebra. You just plug in, you get equations that u dot equals mu u plus v minus 2u squared minus 2uv, and v dot is going to be minus u plus mu u plus 2u squared minus 2uv. That's just some algebra. The point being, so now we have described the dynamics in terms of the coordinates on the center manifold, which corresponds to what we had in the one-dimensional case, where we said we have the coordinates on the center eigenspace, which is here in the 1D case. And then we describe the dynamics in terms of that coordinate. And so as x changes, we actually have the dynamics following the center manifold around here. And so now we have extended that to 2D. It turns out to be useful to rewrite these equations again, because we're expecting oscillations. After all, we have a complex pair of eigenvalues. And so therefore, it's useful to write it in terms of a complex amplitude, which you could construct by just saying A is equal to U plus IV. And then if you plug in, you get an equation for A, which looks like that. Again, this is just algebra, so I'm not going to go through it. I just want to write it down so we see what kind of thing we have in front of us. So it's just a whole bunch of terms. When I just want to make a few remarks about these terms. And there's still minus 1 minus I A star A. So that's a pretty messy equation. But what do we see? Well, it's an equation for A and A star, because U and V are given in terms of A and A star, okay. What we see is if mu is equal to 0, this term is gone, and this term is gone, and the only linear term is this guy. And that shows us that indeed the eigenvalue here is minus I. So it is purely imaginary, and something is oscillating, A is oscillating. Then when mu is not 0, when it's positive, we see a positive growth rate, because the real part here is then positive. And in addition, we see that mu changes also the frequency, because this eigenvalue, the imaginary part of this thing, also changes, mu changes the imaginary part of the eigenvalue. Okay, so that's a typical situation. And then there are nonlinearities. There are two nonlinearities, and these are just some quadratic terms. It's not completely surprising, because we started with a quadratic nonlinearity, and really we didn't do anything except for rewriting in terms of algebra. Right? There's no approximation. There's just rewriting in terms of a different quantity. So we have, again, quadratic nonlinearities as we had in the very original equations. Okay. So what's the point? Well, the first point was, as I said, that this is a general strategy that we want to write everything in terms of the coordinates on the center eigenspace. Here, this looks pretty ridiculous, because we're just living in 2D, and the whole space that we have is the center manifold. And so it doesn't matter how we write it, it's always going to be that there's no simplification to be gotten by doing that. You just rewrite it. So that's true. And in fact, we have not made use of any smallness of anything. We have not said that mu is small, close to the bifurcation point. We have not assumed A is small. We just did algebra rewriting. However, as we will see a little bit later, if we now actually assume that we are close to a bifurcation point, meaning mu is small and A is small, then we can transform these equations with what's called a near identity transformation and simplify it. We'll not do that right away. We'll hold off with that, but that will be an important step. Almost more important is, however, to now think of, well, in reality, we have probably a higher dimensional system. We don't have a two-dimensional system. When we want to do a center-manifold reduction, we're really thinking of some high-dimensional system going down into 2 dimensions. So I don't want to do that explicitly. That's sort of a lengthier calculation, and it's something worthy of a homework, as one would say. And we'll do a homework like that. But let me sort of sketch it how it would work. So if we, let's assume we have a 3D system, just so we have a little bit concreteness, but I'm not going to write down specific equations. So say we have 3D. And so in the original coordinates, that's going to be X and Y and Z. And they're given by, there's some ODEs given for that. So we linearize around some fixed point. We find now, in this case, there's a complex pair of eigenvalues that cross the imaginary axis that characterizes our bifurcation point. And then there's a third eigenvalue. And we assume that is negative because we would like to have only a stable manifold and a center manifold, no unstable manifold. Okay, so then we describe now this XYZ point in terms of the coordinates on the center eigenspace and a coordinate in the stable eigenspace. So I'm going to write it as U times V1 plus V times V2, just like we had a second ago. These would be the coordinates on the center eigenspace, plus W times V3, and that would be the eigenvector with lambda negative, lambda 3 negative in the stable eigenspace. Okay, and then by algebra, we get to rewrite these equations first just in terms of U, V, W. So we would get something like U dot, V dot, W dot is equal to something like an F of U, FU, FV, FW. And each of them depends on U, V, W. Okay, so that's just algebra rewriting. And so now comes the center-manifold reduction step that we say near the bifurcation, we can describe the whole state, all U, V, and W, in terms of only the coordinates on the center eigenspace, right? So that means we say, okay, on the center-manifold, we have W is given by some function, which we called H before, let's call it H again, of U and V. And how do we determine W, this function H? It's again as before, when we had a single real eigenvalue, same strategy. The picture is, again, that we're following the dynamics. The center manifold is invariant under dynamics. So if we are on a center manifold, we stay on it. So the evolution here is described on the one hand by the change in X. Well, now we're on 2D, so in actually V and U and V. And but on the other hand, we also know that the evolution of here, the Y component, or now in this case, it's actually the W component, it satisfies its own differential equation, right? On the one hand, W dot is given by FW. On the other hand, W dot is also given through this equation, which is W dot is equal to, well, let me write it out in completeness. This is going to be a larger expression. So let's do that. So as I said, we have this equation, take the derivative with respect to time of this equation, and then it has to be equal to FW. Okay, let's do that. So we have W dot is equal to dH by du, U dot plus dH by dV, V dot. Now U dot and V dot, of course, are given by FU and FV, and W in there is always given by H. So that's what we plug in. So we have dH by du times U dot. So U dot is FU of U, V, and H, which is a function of u and v. I'm going to suppress it, it's take too much space, plus dh by dv of fv u v h. So that's the evolution of w, because w is on the center manifold. But w also satisfies its own equation already. So we have that this is equal to fw of u and v and h. And so that's now the equation that determines for us, or that we use to determine h. Again, we have the condition that the center manifold is tangential to the center eigenspace, which means that this w is strictly nonlinear, meaning at u and v equals 0, it goes through 0. Excuse me. And its first derivatives with respect to u and v are also 0. And so we do our standard expansion in the coordinates. So we do an expansion in u and v. And order by order, we determine the function h. And once we have determined the function h in terms of u and v, we can plug it into our equation for u and v dot, which then are completely given simply u dot v dot in terms of u and v. We have the closed dynamics on that center manifold. So it's more algebra, and it's another one of these cases where Mathematica comes in really handy, or Maple, whichever one you want to use. Although the first time around, it might be good to do it by hand. Okay, but that's the strategy. And so we see that this should work, and we will then get an equation for u and v, which we should be able to again write in terms of some complex quantity a in this form, and it will give some kind of an equation for a. I mean, we don't quite know what the structure should be. Well, that's not true. Actually, we do know something, because we know the linear part of that equation has to reflect the linear part of the full system, at least with respect to that the center eigenspace. And so again, at the bifurcation point, the real part of the coefficient will be 0, and the imaginary part will give the frequency of the oscillation, and then come nonlinear terms, and we don't know anything about the nonlinear terms. Okay, so that's our not multiple scales. That's what we're going to do next time. This was center manifold reduction for Hopf bifurcation.